I guess I'll call this EM36 Learning How to Learn. I've got a series started that I was going to start to link up the early math to the algebra worksheets that have already been converted. I got to find them. I got probably 600 number of videos I have. I've got probably 5, 10 times that in worksheets over the years. So I got to find things and link them up. But so I'm going to say learning how to learn because I think there are principles that govern the learning how to learn process. I know in college, we were very fortunate. My sophomore year, British International became our coach. I was trying to make that team. I played for the freshmen, and so I was trying to make varsity club, university. And back then we were kick and run. Soccer was just starting in the country, and you'd watch a professional game and go, "What the heck are they doing?" Right? And that's what happened to the hockey players with when they met the Russian team. They had principles of team play from the soccer side of things on the hockey rink, and they shocked the NHL with how well they played and the way they played. But anybody who had learned some of those principles, because I looked up in Webster, he talking about principle of team play. I looked what a principle was in the context of what he was saying, and the fourth definition was rules that govern conduct. Well, I think there are some rules that govern conduct, learning math. One is repeat. Keep looking at things until you understand it. And the other is if you got a problem and you don't know how to do it, can you rewrite it? And I think a good multiple choice, I said that in previous videos, makes that happen. So there was a question about cups of sugar, baking, and what's the difference between something that took 5 1/3 cups of sugar and maybe 4.5. It was something like that. Right? And I presented it to my grandson, and he paused. And I wish I had said, Bryce, if you're not sure what to do with it, can you rewrite it? Because we're practicing those skills, right? So you got 16 thirds minus 9 halves. Okay, and maybe there's still a little bit of a pause. And I said, can you rewrite it? And we're working on seeing this as 32/6 minus 27/6. Okay, now we got somewhere. Because he says that's simple now. All right, and he understands, I think, numerically what this means. And 3 months ago, he didn't. And again, I said, walk 5/6 from this wall to that wall. And he went about 1/10 of the way there. So I knew there was no numerical sense or understanding fractions. In fourth grade, he's got to have his times tables down. We got to still do that. He still has to get his times tables better. And he still has to get his counting skills better. So at some point, I have to abandon this and take a full day or 2 days of nothing but crunching numbers. Okay, nothing but saying, okay, let's add 765 plus 593. Get the column set up properly. I think you'll do that. All right, let's multiply it now. Whew, a lot of just drill and kill, drilling. Okay, so I do understand that. And I also have to talk about unit conversion, feet to inches, then to metrics. So that's got to take a lot of things I'm aware of here that have to happen. But I'm really targeting some early algebra situations that students struggle with. Okay, I'm ranting, I know, I'm ranting. But let's look at problem 1 and what I have in mind there. All right, and at the end of this video, because we started a calculus conversation, I've got to do another layering process with him. I got to get trapezoidal area discussed again, and I got to talk about rates. And I'm going to have a little physical experiment with him. All right, so I got to get back to that. But that's going to be at the end of the video. Okay. All right, so I can erase this so I can get some room. And I think the book is in. I am now doing these, kind of doing them from an easier to harder perspective for what he can do quickly and easily. And then I'm hoping that to repeat this just by changing the numbers. I think lesson set 35, EM35, has that process. But I really have to do this lesson set with him today. So I probably won't even do the previous one because I got to play off of what we did yesterday. And I think that's the art of teaching. All right? And I think that math is an art form. And I think teaching is an art form as well. All right, so let's have at it. Why is it important that I'm asking can you do this first problem 3 different ways? Again, one of the principles of my class is write what's the easiest way of doing things. And it's going to have a significant importance for understanding the conversion process for polynomials, putting things in graphic form. So let me make that connection. At least plant the seed and play the video 4 days in a row, and maybe what I'm doing over here might make some sense. Just a minute a day. Come back to this. All right, so what are 3 ways to do 6 over 3 times 9? Well, you could have done 6 times 9, renamed it, and then divided by 3. That's probably the hardest way to do that problem. Or you could have done what? You could have put 3 into 6 and called it 2 and done 9. That's probably the easiest way. But you also could have done 3 into 9, which is 6 times 3. And all of those are 18. That's actually the hardest way to do this problem. So then I give them the choice. And okay, I got to tell you how that plays into this. All right, so the graphing form for this, if you want to learn it, go to the symbolic rules video, which I'm going to make again, because I made that like 25 years ago, and it wasn't on the internet. I thought I put it on the internet, but it wasn't there. It was just on the school's webpage. So finally got a YouTube channel because of COVID, uploading videos. I just couldn't figure out how to do it quickly with the technology that the school is offering, and working all day long, 4 in the morning till 12 at night, trying to get through the COVID process there, teaching through Zoom. And I just forgot where I was talking. So let's just look at how to write this equation in 10 seconds or less. It's actually 5 second or less problem. And so this is actually x minus some geometric reasons for why I'm doing this. They're in the playlist. And what am I doing? I'm looking at squared change. Squared change. Okay, so if I go over to 10, I've actually changed by 3 units horizontally, but the square change is up 9. Okay, and I don't want that. I don't want to add 9 plus 2 because it doesn't take me to 21. What takes me to 21, 19. Okay, in order for this conversion, you're really looking this way, and you're picking 7 for a number because that makes 0, and that's a nice multiplication, 0 times something, which gets us 2. And if you pick 10, then you're really making 9 units of conversion. And if you, now the next one is the tough one for people to really see this. I need a squared multiple of 9. What's the next squared multiple of 9? It's actually 81. I need 81 units of change. I need the number 81 here in order to divide 9 into 81. And so what makes 81? 9 squared. So what makes the parentheses 9? 16, right? So if I put 16 in here, I get 9, and 9 squared is 81, and 9 goes into 81 9 times. So I'm going to get 9 times 19 plus 2, and that's pretty close to 9 times 20 plus 2, right? So you could do that, 180, take 19 away, 171 plus 2, I think 173. Now I might have done that too quickly, talking pretty fast here to get to the hook of, okay, let's do these quickly and easily, which we will, but I'll still explain how to do them. But I'm expecting Bryce to do this problem in 5 seconds, that in 5 seconds, this in 5 seconds, all of these 5-second questions. That's the goal, where we can say, well, that's simple. Okay, so where am I? I'm back over here, and now he's looking at what's the easiest way to do that. I hope he says 2 times negative 3, and I hope he says negative 6. What's the easiest way to do that one? Well, the prime factors, so we don't have any. You got the choice. You can either say 5 sevenths times 2, or you can say 2 sevenths times 5, which would be 2 times 5 is 10 sevenths. I want that to be a quick boom and know why we're doing it that way. Which is bigger, 10 thirds or 7 halves? Well, the quickest way, he knows the quickest way for that problem. And I will take my time, though, to make sure he understands why it's the quickest way. He's going to say, that's 20, that's 21, then this is bigger. And I'm going to say, yeah, And what's the concept behind it? You just found the common denominator, right? You made that 2 times bigger, so you got to make that 2 times bigger. That's why you only had to do that part. And then in order to make that a 6, you got to multiply by 3. Okay? Yeah, that bigger. Right? And I gave him that because I want him to know that that's minus 1/6. So I might do that as a flashcard. I might do it for him so we can keep this thing going so we're not working for an hour and a half. But it's a flashcard. He's seen it, and he'll see it again on the next worksheet, and then the next worksheet, and then the next worksheet, and then the next. I don't stop. That's going to be on the final exam if it was a class. If this was a 4th grade class at the end of the year, that would be there. One of about 120 questions, and I'm hoping it's 5 seconds. That's this process. All right, 5/4 minus 3/12. Let me get some real space here now. So I'll put each problem on the board. Take more time, slow it down, do the problems out. I wish I could figure out how to write an answer key and upload it. Somebody can tell me how to do that, I'll do it. But I gotta figure out how to do it without a printer here. Okay, where am I? 5/4 minus 3/12. I'm embarrassed by this one. Because I was going to take this and make it 15/12 minus 3/12. And then I went, oh yeah, all I had to do was call that 5/4 minus 1/4. Oh, Lord. But either way, right, I just want to make sure he doesn't do bingo, bango, bongo. 5 times 12 is 60. 4 times 3 is 12. And both of those are over, where am I? 48. And I'm hoping we don't go there. And we'll see. We'll see if I have to talk about that or not. All right. This one, number 6. In the last video, talked about switching the multiplication, putting 25 over 50 because it's commutative, multiplication is commutative, and you know numerator times denominator, numerator times numerator, denominator times denominator. And we certainly don't want to do that right now before we reduce. So is he going to say 1/2? Okay, and will he see 7? I'll tell him if your times tables are strong enough, you will. Otherwise, you're going to have to work harder. I'm going to leave it at that. Okay, 2/6. All right, and obviously that then is what? Would he have seen 14 into this as 1/3? I might have to play with that a little bit with him because initially talking here, I should have seen 14 as 1/3. I probably would if I wasn't talking to him, but maybe I play with that a little bit with him. Okay, we'll see. And he knows 1/2 times 1/3 is 1/6. He's got that down quickly now. He didn't 3 months ago. Okay, 34 over 100. 0.34. All right, just going to move it 2 decimal places. And if he doesn't do that, I've got a new refrain for him. I'm going to say, well, maybe you'll remember that tomorrow or the next time we work. Because we are doing mnemonic devices now. Right? We're doing SO. I did finally do this again with him. And I gave him 2 new words, YOU. So he's got succinct, he's got omnipotent, he's got nefarious, he's got optimal, he's got winsome, he's got yoke, and now I gave him obscure and ubiquitous. Learning how to learn. Right? If he looks at those every night for 1 minute, they'll be part of his vocabulary. And I'm going to make him I'm going to get some definitions and some sentences of usages. And I'm going to start making him a journal of new words so that he can build his vocabulary. And it only takes 2 minutes to start reading that at night. And if you keep reading it every now and then, you don't have to, but maybe every week after that, learning how to learn. Okay. Minus 1/5 cubed. Okay, I'm hoping he realizes that it's minus 1/5 times minus 1/5 times minus 1/5. So he knows the negative is being cubed. He knows the 1 is being cubed, and he knows the 5 is being cubed, so I hope he says minus 1 over 125. And if I have to spend time with it, I will. A complex fraction, we're over here now, 30 divided by 15/8. Hopefully I'm linking these on the internet properly so that you can have the worksheet in front of you and you can follow along a little bit better. So will he immediately do 30 times 8 over 15? Can we get to the point where if you divide a number by a fraction, it's the same as multiplying times the reciprocal, or will I have to show the division to him? I don't know. I mean, he's got a whiteboard. I can see his work. So if he does this first, where am I at? I forgot. 15/8, sorry. 15/0. If he does that first, then I might say, well, geez, if you know division by a fraction, multiplying, maybe you can skip that step. We'll see if you remember that the next time we work. We're always going to hear that a lot on this one. Can't wait. So now we're at $80, 35% off. How much does it cost? I think the easiest way to do that is find 10%. So 10% of 80, I'm pretty sure he's going to say $8. And I'm going to say, okay, how do you get from 10 to 35? Well, you got to triple it to get it up to 30. So what's $8 tripled? 24. Now we got to get 5%. How does 5% compare to 10%? It's half. What's half of 8? 4. Okay, so where was I? 24 and 4, 28. Can you subtract 28 from 80? Can you take 20 away from 80 and take another 6? Guess it costs 54. Gonna have that discussion. Okay, there's other ways to do it, but that's easy. And now 1140 to 223. And I think he organically started counting up from 1140 to get to 223. And I pointed that out in the previous video when you're counting money. If somebody gives you a $20 bill and something costs $5.75, for instance, right? You got to give them change back, right? They're giving you a 20. You got to give them change. So what are you going to give them? Well, you're going to give them 25 cents. That gets you up to $6, right? You're going to give them another 4 to get you to $10, and then you're going to give another 10 to get to 20. That's how you should do change. Count up. Looks like you got $14.25 going back to that customer. Just going to plant the seed there. So 1140, you got to go up 20 minutes to get to 12 o'clock. From 12 o'clock to 2, you got 2 hours, and then you got to add another 23 minutes. All right, well, those are the like terms. Again, you can't add unless you got things that are alike, so you better add minutes. And 23 and 20 is 43, so it looks like it's 2 hours and 43 minutes of elapsed time. Now, I hope I'm not making any mistakes here, because I've been up since 4 o'clock, and it's close to 7 now. 2 cups of coffee. Good blood pressure right now. Probably can tell the rate at which I'm talking. That could bring us back to the calculus concept. Looks like I missed a problem here, problem number 3. Not going to start again yet. So 63 over 77. He doesn't immediately see that as 9/11ths. I can guess what I can say. Wow, Bryce, if you knew your times tables better, you would have spotted that. And then I'm going to print him out a sheet today with the 1, those boxes. 1 times 1 is 1, 1 times 2 is 2. I'm going to make that. I'm sure there's got to be one on the internet. So I don't have Wi-Fi here. So I go to the local library, search for that, and then I'll hand it to him right at that instant. And if he does say 9 over 11, I'll congratulate him. I said, you know, your times table's better now. But I'll wait till I spot where he hesitates, and then I'll hand it to him. Spend some more time looking at this. All right. The other thing I'm going to do is if he counts on his fingers at all, if he doesn't build up, certainly if he starts counting there, I'm going to have a spatula handy, and I'm going to tell him before we start. Of course, I'll miss it. Don't worry, I'm going to miss it, right? But I'll go, oh, I missed you. I'll get you next time. You don't know I'm kidding, right? But he's going to start. Going to make him do that. All right. God, guys, on a roll here today. Where am I? Yeah, that's another question altogether. X equals 2, y equals 7, z equals, I'll see if he draws it in standard position, because I'll ask him to. And keep talking about, we're going to draw triangles all over the place in this circle. Sometimes we're going to put them over here. In fact, we're going to do that in this video. And see if you can estimate the sine of 3. All right, because very few students come out of pre-calculus after studying trigonometry who can give you the definition of a radian. So I'm not waiting until he gets there. God, I got years to talk about it with him. He'll understand what a radian is. I think he already does. All right. So 2, 7, 2, 7. Oh no, z was, y was 7. I gave him y was 7. Angle A, right there, right triangle, 49 and 4, 53. He's going to get that quickly. He's already showed me he's got that in his pocket. What's the sine of angle A? I'm just going to shortcut this. He knows it's 7 over root 53. He knows the cosine of angle A is equal to 2 over root 53. And he now knows the tangent of angle A, I wrote that one out, is 7/2. And then I'll erase this. Then what's the slope from here to here? Because we're starting to talk about the slope of these line segments. Yeah, it's 7 over 2. And that's the change in y over the change in x. So I'll write that. And that's how we say how something's increasing or decreasing. Yeah, and I'll draw the tangent line to some curve, maybe zoom in on it soon, so he sees the linearization process. All right, so he's got that down. And why does he have it down? Because we started 2 months ago looking at the Pythagorean relationships. The sum of the squares of the smaller sides of the triangle, right triangle, add up to the square of the hypotenuse. I'm saying that better. Right? First time I said that, I was like the scarecrow in the Wizard of Oz. And I'm still not sure what he said. Right? But I got it down now. Because why? I'm repeating my explanations. The same way he's repeating looking how to do something, I'm getting better at explaining it. Because I keep saying it. All right. So, where are we at? 40°C. 40 degrees Celsius. What is it in Fahrenheit? I'm not going to prompt him at all. I want to see if he writes 9/5 C plus 32 equals Fahrenheit, because just a lesson set ago he said 5/9. I said, well, that would be part of converting Fahrenheit to Celsius, but we're converting Celsius to Fahrenheit. And I think he's going to be pretty darn good at throwing a 40. Well, here's another example of conversion. Celsius, I might start saying, what's Celsius degrees divided by a Celsius degree? It's a generic 1. What's 10 Celsius degrees divided by Celsius degrees? It's generic 10, because those symbols cancel out of the problem. They don't cancel out, they become the number 1. Okay? Planting a seed for physics. All right. 8, 72, and 32, 104. We'll see how quickly he gets there. And then I give him 95 degrees Fahrenheit. 95 degrees. Is that what I said? 95, yes, 95 degrees Fahrenheit. And I'll just go through the mechanics with him. All right? And he knows if something plus 32 equals 95, then he's doing this in his head. He's taking 32 away from 65 to take 30 first, 65 and another 2, 63. And now I will probably write this. Well, this is where you're at, Bryce. You have a choice. Do you want to do the inverse of multiplication, or do you want to multiply 63 by 5? And in this case, I hope he divides that and says 7. And now we have C over 5 equals 7, and that brings us to what? Celsius, 35 degrees. Celsius degrees, 35. 35 Celsius. And then we'll come back and check it. Let's check it. Well, there's that again. 7 times 9, 63, plus 32. And I'll say, well, what's 2 plus 3 plus 30 plus 60? Maybe I'll write that. And I hope you do the 30 plus 60 and you know what 2 plus 3 is. Okay, and if he doesn't write the equation, Guess what I'm going to say? Oh, maybe you'll remember it the next time we do this work. Oh, I'm getting nasty. We have a great relationship though. So what's the product? 64 minus 25. Okay. It's going to be fun. All right. Guess what I'm going to say if he doesn't remember this? Once he does the square, I know he's going to, if I prompt him, I know he's going to do that. I know he's going to work with this. I know he's going to work with that. And will he say that this is equal to 8 plus 5 times 8 minus 5? Well, what do you do in calculus, in Algebra 1? You factor x squared minus y squared. Of course, I think in the textbook they more likely work with a and b. All right, but I think I'll stick with x squared minus y squared. And I'll say, well, isn't that x plus y times x minus y? I think I can do this. I didn't anticipate it, but I think we can multiply that and say, what's x times x? I think he'll say x squared. And if he doesn't, I'll shut down the variable work. All right, I'll back up. All right, if he doesn't follow that, I got to back up and just stick with the numbers till we get to variables. I think he'll say that. And what's minus y times x? Minus xy. What's y times x? xy. What's y minus y? Minus y squared. Well, guess what? He'll say that's 0. I think. Okay? But maybe I got to do it here. Right? Maybe I got to 64 minus 25, got to do it, 44, 39. Right? And so what's 8 plus 5? 13. 8 minus 5, 3. I'll make these connections. Well, that's 39. So that is the product. And maybe I've got to actually do it out still. I should. Because my belief here is that I want to mimic everything you study in algebra with numbers instead of going from the generalization to the concrete, which we don't do enough of at the algebra level. I'm going from the concrete to have him generalize. So 8 times 8, I call it double distributive. So I hide the 5. Say do that first. 64 minus 40. Okay, now we'll bring the plus 5 in because we got a whiteboard up. I wrote 2. Plus 5, well that's 40. And I want to definitely do this. I wanted to see that before I go to x. So I don't want to go to x. I'm not going to do x squared minus y squared yet. I'm going to do that. Okay, so these videos are helping me anticipate what I'm going to say to him when we do this today because he doesn't have school today. So I'm getting 2 days in a row. Make some gains. All right, where am I at? I'm at, I think I got out of, did I do this? I don't even, yeah, I did those. I did that. Yeah, okay, I'm fine. So, well, I'm not. Anybody knows me knows I'm not fine. All right, so I'm over here, getting our rules of exponents. 2 to the 7 over 2 to the 3. Let's see if he says 2 to the 4. And if he doesn't say 2 to the 4, then I'm going to have to write 2 times 2 times 2 times 2, 4, 5, 6, 7, and I got to multiply another 3. I got to put it on this side. 1, 2, 3. Count them up. We did 10 here. How many are we going to do below? No, that's all we're doing. Right? So there's 2 to the 10. It's this one where I'll leave that now that I've done this. I'll leave it. I'm not going to erase it. Okay, and I'm dividing by 2 to the 3. Well, he's going to see that. I know he is, and he's going to say, oh, that's 2 to the 7. So that was intentional. Right? So I'll say, yeah, and I'll look at that answer. 2 to the 7, and I'll say, division by 2 to the 3 is the same as what? Multiplication by 2 to the 3 on the other side. Right? Because solving equations, I don't do the same thing to both sides. No, I just say, what's the inverse operation? What's the inverse operation? It works much better than writing everything out. It gets the brain sharper, seeing that happen. So what's 2 to the 3 to the 4 will only be the second time you've seen that, and we'll go to strict definition. I'm definitely going to want to write this out, even if he says 2 to the 3 to the 4 equals 2 to the 12. I don't think he will. So I'm going to say, okay, you've got 2 to the 3. What's that mean? 4 times. Okay, maybe he'll add those up. If not, I'll do it. There's 3, another 3, another 3, another 3. I'll take the time to write that out, right? Because this is his foundation. He's got to have those rules of exponents down to get to higher level mathematics. And I'm not taking any chances that he won't be able to do that. Okay, 22 is a big step up for him. Big step up. I've been planting the seed with him seeing log base 3 of 9, problems like this, been doing this for quite a while, and he knows that's true. That's great. And I have been writing it this way. And I want him to see that that's also 2 because log base 3 is all about the exponential activity on top of a 2. So, what is the problem with doing this? They're not the same base. Pretty hard to see exponential rules if you don't have them the same base. Is there some way that we can answer 4 to the x equals 8 by changing the bases? I don't expect him to do it, but the conversation has to start. I've got to say there's another way to write 4. 2 squared to the x equals, oh, that's 2 to the 3. He might say that. And I'm going to say, yeah. And what does that become? That becomes 2 to the 2x. Jeez, I'm tired. 2 to the 2x equals 2 to the 3. What has to be true? That 2x equals 3. Oh, x has to be equal 3 halves. All right, well, let's look at x equals 3 halves. Now let's go back to the original problem here, right here. Let's look at 4 to the 3 halves, and let's figure out what that is. He might know, because I got a cheat sheet that says that's square rooting, right? So I've been pushing that. And maybe I say, yeah, what's the, eventually I'm going to say, what is the square root of 4? And what happens when we cube it? And that's what's going to happen here eventually. But I think he's going to look at 4 to the 1. I think he's going to look at 4 to the 2. And that's going to be 4. That's going to be 16. And we'll have that little game of, let's guess. And he's going to say, I don't know. He may do this. If he does, God, I'm going to be thrilled. But I got a feeling he's going to have to work with the calculator but after he takes a guess. And if he takes some decimal in here, I don't know, crazy answer, I'm going to say it's 8. And then we'll go to the calculator and check it. How much we're going to have to talk about that, I don't know. But I want to have the conversation started, and I'm just going to keep the conversation going until he gets it. It may take weeks, it may take months, it may take they already have it. We can find out. Okay. And now I'm trying to build the log rules. Log base 3 of 3 to the 9 over 3 to the 2. I'll say, can you figure that one out? Again, if he's stuck, I'll say, is there a way to rewrite that? One of those principles of learning. 3 to the 7. I think he's going to get there. And so what is this thing asking? It's asking, what do you put on top of 3 to get 3 to the 7? Who's buried in Grant's tomb? Okay. So that's the first 23 problems. And I would expect that a month or 2 months from now, most of those are going to become 5-second questions for him. If we keep repeating. The same way you kind of memorize your times tables, you don't have to think. Get to the point where you don't have to think with this stuff. You just recognize it. You know what to do. It takes time. Some students pick it up very quickly, some don't. But everybody makes gains through the process. All right, so he's hooked. Now that we're going easy to hard, he's going to start seeing that he can put his answers down very quickly and easily. Okay, so another exponential. So what's the way to rewrite that? 5 to the 7 times 5 to the 3 is 5 to the 7 plus 3. Okay, 5 to the 10 in the numerator, 5 to the 6 in the denominator. Cancellation, I'll use the word, but what word should I use? Creating ones. I mean, what's another way of writing 5 to the 10? 5 to the 6 plus 4, right? And what's another way of writing that? 5 to the 6 times 5 to the 4 over 5 to the 6. Well, we don't have to do that. We get an answer of 4. So, how much of this am I going to have to say? 5 to the 10 over 5 to the 6, 5 to the 4. How much? I don't know. But I think he's going to get here maybe already, quickly, easily. But I might still layer it. Nice term, layer it with that explanation, because I want to make sure his foundation is sound. All right, so now we're looking at to the nearest. I don't remember what I wrote on the sheet, but I might say, and this is a great multiple choice question. I'm going to do some multiple choice with them. As I said, I'm going to try to find something that I can cut and paste so we get some word problems, the ones that I think he needs to see. And I think I'm going to do California grade 5 with him. Problems 11 through 16 look like they were good questions. What year was it? I don't know. But thousands, hundreds, tens, ones. How are we getting from thousands to hundreds to tens to ones? Yeah, we're dividing by 10. And if I divide by 10, I got a tenth. I got a hundredth. If I keep dividing by 10, I got 1,000. All right, so let's say the nearest one. Okay, well, you got 7 tenths. Are you closer to the number 7 or are you still closer to 6? I hope he puts a 7 here and says 0, and yeah, go ahead, put a 0 there, but don't write the rest of them. Okay, you do that, I know you know what you're talking about. All right, so will I do this? I was going to do the layering of the cubic for calculus because we had a great conversation. So what's the area of a circle of 10? I hope he says 105. Okay, so radius is 10, right? You square it, you multiply it times pi. Might have a little more chat by that, and that gets you this area. How do I make that area bigger? Put another layer on it. Huh? What did I just draw? Circumference of the circle. What's the circumference of the circle? 2 pi r. I'm going to stay away from this discussion, at least for another month, because there's too many skills here that are basic that he's got to learn. So I'm going to stay away from that. But that's where I'm going, and we'll do the numerics to prove it, because we'll snip, open it up, and measure it as a rectangle. Great conversation coming from that. No, I don't want to do it yet. I want to do the little layering process with the cubic here. I think it's easier for him to see. And I'm just going to talk about it conceptually. I'm not going to do it out with him much, but that's at the end of the video here. All right, so if he says 100 pi, I'm just going to move on. I'm going to ask him where 1.57 radians are. I think he knows. And then I'm going to say, yeah, it's pi over 2, right? And you could, pi is 180 degrees of change, and you're cutting it in half. And so we're getting close to working with the unit circle, finding the sine of pi over 3. I'm going to hit him with the equilateral triangle and the 60-degree angle being bisected. And so if you want to see that, go to the trig playlist and look for the introduction to the unit circle. All right, so getting there. All right, so 1.57, I don't think I'll, maybe I say, so what's the sine of pi over 2? No, I'm not going there. There's too many problems here. It's coming. It's coming. I don't, at this point, I probably got to have him run around the house once or twice to get away from this and come back, because I do want to finish all of these. What's 1 radian? 57.3 degrees. And if he doesn't remember that, I'm going to go, well, maybe he'll remember it for tomorrow. Forgot to say that on one of the other problems. Sine of 3. At this stage, this is getting really long. Might might skip that. Where's 3 radians? I'll come back to that later. 4, 7. Okay, coming back to the perpendicular. So 4 for x, 7 for z. What's y? I hope he says 49 minus 16 square root of 33. All right. 1, 1 to 5, 2. He's getting very good at plotting now. 1, 1 to 5, 2. And I'm asking what the slope is between those two coordinates. Pretty soon I got to write the equation in the line form. So 1, 1. I'll just do it here. 5, 2. 5, 2.
So it looks something like that, right? And I just wanted to see the change in x, and I'll put 5, 2 here. So 1 to 5, change by 4 horizontally, 1 to 2, up to 1. So you're going up at a 1 to 4 ratio. Okay, we'll do that. Next user-friendly number. Well, I shouldn't have. What was it? What was it? Oh, 1, 1, 5, 2. I want to have to draw that again, right? And so what if I do the same thing? What if I go over 4 and up 1? Well, how far is it from 5 to 9? That's another 4 and up 1, and I'm getting a linear function.
Getting a graph that looks like a line. Because it is.
Okay, so I wanted to start seeing that. And I'll keep morphing that into eventually how to write the equation of a line quickly.
Now, the reason I went to this with 1993 is I had an Algebra 2 class, and 6 out of my 16 kids didn't write the equation of a line correctly. So the next year is when I started this whole process of, I'm going to do it every day. And I did it every day. I've had maybe 1 or 2 students who didn't understand the conceptualization of how to write the equation of a line since then, since 1993. Everybody. First question I ask on every test, write the equation of a line. And sometimes somebody makes a math error. You know, how far is it from 3 to 10? Might say 6. You know, because usually the first problem, sometimes on any test, kids are a little anxious. You know, occasional error in counting, right? But everybody's got the framework down correctly since 1993. Okay? And it's usually 5-second calculation. So doing it every day, magic. All right? So then I said to myself, well, if that's the case, let's link it up with other things we do every day and do it quickly. So that's why every problem I cover is on every final exam. All right. 82% is a decimal. I hope he says 0.82. Right? If I have to do 82 divided by 100 and move it, I don't think I will, but if I have to, then I'm going to go, oh, maybe you'll remember that tomorrow. I'm really going to have fun with that. I want him to learn scientific notation. He's been practicing this, and I'll say scientific notation is taking the digits and writing them as a decimal between 0 and 10. Okay, so we write that as a decimal between 0 and 10. And now we have to ask ourselves, if it's there, how do I move it there? I've got to go 1/10, 1/10, 1/10, 1/10. So I'm going 1, 2, 3, 1, 2, 3, 4. So that's the same thing as that. Okay, now that's new for him, so I'm going to have to actually spell that out. What's the area of the triangle? The base is 9 and the height is 6. He'll do it out. He'll do a base of 9, height of 6. He'll say, well, that's half a rectangle. And I'm going to say, Bryce, it's on your cheat sheet, 1/2 base time height. Do you really have to do that, or do you think you can cut, he's going to say 54 cut in half, what, 27? Right? Couldn't you cut the 6 in half and made it 3 times 9 and say 27? Maybe you'll remember that if we do it again tomorrow. Oh, boy, I got to... I gotta have some fun. At some point, it's cruel, so I gotta stop at some point, and I gotta keep an eye on that, and I gotta back off. All right. 81 to the 1/2. Maybe I'll pick and choose. Well, if you know that 1/2 means take a square root of 81, I guess you don't have to work hard anymore. 81 is the area, right? And that's side, and an area has 2 side lengths. That square has 2 sides. It's got 2 sides, and you're looking at one of them. Not sure that language is something I should say, but it seems to work. I'm going to use it. All right, just some straight addition and subtraction, and I definitely want him to see 10 plus 9 is very close. 2 plus 9 is very close to 2 plus 8. So he's got 10 plus 20, 30, plus another 30, 60. But 9 is a little bigger than 8, right? So anyway, I'm just trying to get him to group things. All right, 7 times what cubed plus 7 is 11. This one I'll probably write out. Boy, I wish we had a big whiteboard so I could have all these questions in front of him, so he could just
go around the room, but don't have it anymore. So where am I? I'm at 7 times what cubed plus 7 equals 11. And I'll say, is there an easier way that I could have written this question? It took me a while to write the word what, and that'll bring us right back to, oh, guess what the letter X is in Arabic? It means something. And I wasn't going to take the time to write it because I didn't want to, but I will here. So something plus 7 equals 11, and he's gotten to the point where he knows that's got to be 4. So that means 7x cubed equals 4, and he knows 7 times something equals, what did I give him here? I want the numbers to work more easily here. So where the heck am I? Oh, cube root. Yeah, we're going to take a cube root, right? So, but I wanted division. I got to change this problem. Maybe I had a different number here, maybe a 2. Well, let's put it as a 2. Let's put it as a 3. I got to change this. 2 cubed is 8. 24 plus 7, 31. So I got to change that to 31. All right, I'm not going to get hung up at this stage with fractions and everything else. God. So eventually we're going to have what? We're going to have 3x cubed. I don't like the same numbers anywhere but showing up early on, but they're here. Plus 7 equals 31. Now I'll show you where I'm hoping to get. Jesus, I'm tired. But no, that's correct. Equals 31. All right, I want him to subtract 31, 24. I want him to divide by 3, 8. And I want him to take the cube root of 8, which is 2. That's where I'm at, is that thought process.
Inverse operations. Very helpful when you're working with e to the x, ln of x. You learn the inverse operations. Kids have some success solving some more difficult questions more easily. All right, so that's what we're going to be after. Trapezoidal area. Oh, Lord, this is a long video.
But as we continue with this worksheet,
I won't have to say the explanations anymore.
I'm going to remember lesson set 36, and I am going to tell people, I'm going to refer
To that video where I take time to explain things, because I'm going to stop explaining them. I'm just going to get practice in so that this thing becomes a 20-minute worksheet and not an hour. All right, so 36, where the heck am I? Trapezoidal area.
I'm going to ask him to find the trapezoidal area under y equals x squared from 2, x equals 2, to x equals 4. Okay, and I want him to, it's kind of hard to draw the trapezoid, but yeah, it's just a little bit bigger than the actual area if we're using calculus. 2 to 4, so that's 2, 4, 4, 16. All right, and then he's going to have to learn the trapezoidal rule, which is what? And I'll build this out. So 2 to 4, this height is 4, this height is 16. What's the rule? Width, I've got more room. Width divided by 2 times the altitude on the left plus the altitude on the right, and I will repeat, it's the average of those two rectangles. That's why we're dividing by 2. Okay, let's start there. So 20 divided by 2, it's 10. All right, the width is 2. Sorry, I just said the wrong thing. The width is 2, so 2 divided by 2 is 1. 4 plus 16 is 20. That's the area. And then I think I'll take the time to say, okay, what's the area of that? What's 2 times 4 is 8. What's the area of the triangle? 32 cut in half is, where am I? I'm tired. Oh, Lord. All right, I'll take my time with it. This is where my brain is starting to shut down. I'll take my time with it. So from 2 to 4, if I go up 4 units here, and I go up 4 units there, and that's the rectangle. That's 8 units. See, my scales are all off. That's what's giving me a hard time here. So that's 8. I still have a width of 2, and now I'm going up to 16, which means that's 12. That's where I must have made my mistake. Okay? And I got half of half of 24, so we get rid of the 2, so that's 12. And 12 and plus 8 is 20, and that was what we had a minute ago when we applied the rule. The width, 2 divided by 2 becomes what? The altitude on the left. The altitude on the right is 16, right? And there's our 20 from that perspective. Where's the nursing home? All right, and now I was going to show them the layering process for the cubic. And I'm going to say, what's 2 cubed? I'm just going to do this. I know this is a long video, my apologies. They will, I promise, the next 4 videos are going to just be pump out the answer. It's time to just get to drill and kill. What question am I even asking? Oh yeah. So I've got it. Look at the cubic. I'll start with 2. I'll cube it. And I'll say, Bryce, 2.0001 is 8.0012.0006.0001. And from our conversation the other day, I'm going to say, this is the error of the drawing. So what is the rate of change? It's 0.0001, the change in x, over the change in y. And again, not going to teach it at a, let's repeat a problem. Let's not going after that. This is a marathon, not a sprint. Just putting some things in his head. Now I've got to give him the picture. So Bryce, you correctly identified the layering process in calculus the other day. I was doing layers, and you have to go to that video if you want to see what I'm talking about. So let's look at a box. Let's say it's a 2 by 2 by 2. That's a volume of 8. And here's the layer. It's like I paint 3 sides. And I'm not going to continue this unless he's really got some energy, and I doubt he's gonna. So what are you looking at? Well, that's a square. And 2 times 2 is, let me do it here. You're looking at 1 square. 2 times 2 is 4. And remember, you've got to change, right? That's the 0.001. That's the thickness of this cardboard. We're going to call it very thin, 0.001. So that means that you have 0.001 times 4, which happens to be 0.00, I think I got 4 decimals, 04. And guess what? There's 1. Well, guess what? You got another square area times 0.001. That's another 0.0004. And then you got the last one, 3 of them, 0.0004. And that's 3 times 0.0004, which is 0.0012. Oh, must be a coincidence. That's where I'll stop. And I say, Bryce, I'm tired. Let's talk about that again tomorrow. Just let it sink in. That's got to really take time. I mean, that might be a year for a kid this stage to, I don't know, maybe it'll be a day or 2. I don't know. I haven't taught this age level. I didn't expect to be here 36. I mean, remember, this has been little more than 3 months. And he didn't know what 5/6 of the distance from this wall to that wall was. Look at what we're talking about. Never expected it. All right, 54 minutes. Oh my God.